In this video, we're going to learn how to find the sum of a geometric series. First question is we want to compute the sum of the first 12 terms of the geometric sequence 5, 10, 20, 40, and so on. Now, one option would of course be to just find all of the terms and add them up. But that could take a while in some cases. Imagine if we wanted to find the first 100 terms. Is there any better way to do this? In fact, there is. There's a formula. The sum of the first n terms of a geometric sequence is given by the following formula. A1, the first term, times this fraction, 1 minus r, the common ratio, raised to the nth power, divided by 1 minus r. So this is what we're going to use to find the sum of this series, and we'll also use it for the following problems as well. So keep this in mind. Now let's apply this formula to the situation at hand. First of all, how about that A1 term? What is that in the sequence? Well, that's just the first term of the sequence, which is 5. So A1 equals 5. Alright, then how about r, the common ratio? Well, let's look back to our sequence. What are we multiplying by every time? Well, 5 times 2 makes 10. 10 times 2 makes 20. 20 times 2 makes 40, and so on. So the common ratio, r, is 2. And then n, that's how many terms we want to add up, and we're told that right here in the problem statement. N equals 12. We want to add up the first 12 terms. So we'll just plug this into the formula, and that'll give us the sum. A1 is 5, so 5 times the ratio 1 minus the common ratio r, which is 2, to the nth power, so to the 12th power, divided by 1 minus 2. We can just punch this all into our calculator, and the result that comes out is 20,475. So there we go. There is the sum of the first 12 terms of the geometric sequence. Alright, how about a few more examples? First of all, we want to compute the sum of the first 9 terms of the geometric sequence -2, 6, -18, 54, and so on. And again, we'll just use the formula. The formula is just A1, the first term, times 1 minus r, the common ratio, raised to the nth power, and is how many terms we want to add up, over 1 minus r. And we'll apply that to this situation at hand. In this situation, A1, the first term, is -2. So A1 equals -2. Now r, the common ratio, that's what we're multiplying by every time. So what multiplies -2 to get to 6? Well, it's got to be -3 times -3, and then 6 times -3 makes -18. Yeah, that works out. And so we're just multiplying times 3 all along, so the common ratio, r equals -3. And lastly, n, that's how many terms we want to add up, and it's the first 9 terms, so n equals 9. We put all this together and plug it into the formula. A1 is -2, then times the fraction 1 minus the common ratio, -3, raised to the nth power, so raised to the 9th power, over 1 minus the common ratio, 1 minus -3. And the result, this is equal to -9,842. So there we go. There is our sum. Alright, on to the next problem. Compute the sum of the first 15 terms of the geometric sequence a fourth, a half, 1, 2, 4, 8, and so on. So we'll just use this formula again. A1, the first term of the sequence, that's right here. A1 equals a fourth. Now the common ratio, that's what we're multiplying by every time. It's easy to see at this term 1 times 2 makes 2, 2 times 2 makes 4, 4 times 2 makes 8. That also works going backwards. A half times 2 makes 1, a fourth times 2 makes a half, so r equals 2. And then n, that's how many terms we want to add up. We want to add up 15 terms, so n equals 15. So we just take all that and stick it into the formula. A1 is a fourth, times the fraction 1 minus the common ratio 2 to the nth power 15 over 1 minus the common ratio 2. We stick this into our calculator, compute it, and the result is that this is equal to 8,191.75. So there we go. There is the sum of the sequence. Alright, so now we know how to use the formula for the sum of a geometric series, but where does it come from? Here we want to derive the formula for the sum of the first n terms of the geometric sequence having the first term a1 and common ratio r. So where do we even start? Well, why don't we write down the most basic expression for the sum? We'll write that the sum, call it s, is just equal to all of the terms added together. a1 plus a2 plus a3 plus so on, all the way up to an. Now let's try to manipulate this expression a bit to simplify it. Since we know the common ratio is r and we know the first term is a1, we can express all the other terms in terms of a1 and r. So why don't we do that? S equals a1, the first term, and then the second term, a2, that's just r times the first term, a1. So plus r, a1, then a3 is just r times the previous term, which was r, a1, so this becomes r squared, a1, and we keep on continuing that pattern all the way up to r to the n minus 1, a1. That's what an is. Now notice what happens if we multiply this whole equation by r. If we compute rs, that's the same as multiplying all of these individual terms by r, so that's just r a1 plus r squared a1 plus r cubed a1 plus so on, continue the pattern all the way up to r to the n a1. There's a whole lot of terms in common here. ra1 pairs with ra1, r squared a1 pairs with r squared a1, r cubed a1. Instead of these dot dot dots, there would be an r cubed a1. It would really be the next term right after this r squared a1. And then inside of these dot dot dots, there would be an r to the n minus 1 a1. It would be the one right before this one, and that would pair with the ending term of this expression. So here's the magic move here that'll simplify the situation drastically. We're going to subtract this bottom equation from the top equation, and that will cause a lot of terms to cancel. So on the left hand side we have s minus rs, and that's equal to, why don't we just write these terms in vertical order just to be very explicit and see where the canceling is happening. So a1, then minus ra1, then plus ra1, then minus r squared a1, then plus r squared a1, minus r cubed a1. Continue this pattern of pluses and minuses. Then we've got a plus r to the n minus 1 a1 and a minus r to the n a1. And now here we can see that a lot of terms cancel. Here's a pair, negative ra1 and positive ra1. These cancel. Another pair, negative r squared a1 and positive r squared a1. These also cancel. Then negative r cubed a1, and continuing the pattern through the dot dot dots, the dot dot dots would contain a positive term that would cancel with this negative term. Likewise, for this positive term, r to the n minus 1, a1, there would be inside of the dot dot dots a negative term that would cancel with it. So that would go away, and we would be left with just a1 and minus r to the n a1. Before we go on, notice that you can also see the canceling diagonally when you place the terms vertically. So this ra1 cancels with that ra1, r squared a1 cancels with that r squared a1. Inside of these dot dot dots, there's a term that will cancel with this r cubed a1. Inside of these dot dot dots, there's a term that will cancel with this r to the n minus 1 a1. And all the intermediate terms would cancel as well with these diagonal lines. So really, after all the canceling is said and done, all we have is that s minus rs is equal to a1 minus r to the n a1, that term way over there. So now we've got a nice compact equation and we just want to solve for s. So let's go ahead and factor that out of the left hand side. Factor out an s times 1 is s, then s times minus r is minus rs. And then on the right hand side, notice that we can factor out an a1. So a1 times 1 makes a1, a1 times minus r to the n makes minus r to the n a1. Now we can just divide both sides by 1 minus r and get that s is equal to a1 times 1 minus r to the n over 1 minus r. And just to clean that up a bit, make it a little more elegant looking, we can write it as s equals, pull out that a1 in front, and then combine the parentheses on these fractions, write it as 1 minus r to the n over 1 minus r. And there we go. There is the formula. So now we know a quick formula to compute the sum of a geometric series. In the future, we'll continue working with geometric series, which will be very helpful when we try to start modeling real-life situations with geometric series.